Having looked more closely at the nature of the active site in our last lesson, we can now better appreciate how key active site residues participate in the catalytic mechanism of chymotrypsin. As we examine the mechanism of chymotrypsin, we will see that it involves nucleophilic attack by the oxygen atom of the serine side chain. Recall from organic chemistry that nucleophiles are electron-rich and attack electrophiles, that is, those that are electron-poor or may carry a positive charge or dipole. A space-filling model of the active site residues below, overlaid on the ribbon diagram of the enzyme, shows the nature of their close proximity. The figure below illustrates the steps involved in the first stage of the chymotrypsin mechanism, formation of the covalent enzyme intermediate with the release of the first product. On the left we can see the importance of the positions of the serine and histidine residues, and the positioning in the active site of the peptide bond to be broken. The histidine first extracts a proton from the adjacent serine residue, making it even more nucleophilic. The serine oxygen atom then attacks the positive dipole on the carbonyl carbon of the peptide bond. The result is the formation of a tetrahedral intermediate on the right of the diagram. Note the formation of an unstable carbanion in this case, and the fact that the histidine residue now carries a proton. The first stage of catalysis is completed with the release of the C-terminal portion of the peptide. Note that the histidine has donated its proton to the amine group of the peptide bond, stimulating the breaking of the peptide bond and the acylation of the serine residue. We now have the covalent enzyme intermediate. The peptide bond has been successfully broken, but the enzyme must be returned to its original form. The second stage of the mechanism is essentially a repeat of the first stage: proton extraction, followed by nucleophilic attack, followed by proton donation. In the figure below, we can see that a water molecule enters the active site and provides the nucleophile that attacks the carbonyl carbon of our acyl enzyme intermediate. Histidine plays its part again by extracting a proton from the water and thereby enhancing the attack of the O atom in the water. Note that we again have a tetrahedral transition state intermediate. As the hydroxyl group from water is added to the carbonyl carbon, it breaks its bond with the serine residue. Histidine then donates the proton it received from water back to the serine residue. The enzyme has now returned to its original form. As you can see from this example, enzyme catalysis can often include multiple steps, making the speed of these enzymes even more remarkable.